Hello, welcome to this session on PLLs. In the previous session, we talked about the acquisition ranges in PLL, acquisition ranges range for PLLs, and here we discussed about hold in range, lock in range, and pull in range. Okay, now it's time to work out that how we can find the different ranges for the PLL, different ranges for the frequency acquisition. By the way, when we are talking about the acquisition here, it is referring to frequency acquisition. Okay. So, we will continue with our simple example for the PLL, which had the mixer followed by loop filter, which was followed by VCO. Okay. We have seen this example, we have been studying this example from the beginning. So, it is always good to figure out all the things related to that example PL. Okay. So, here V in and V out as shown. Again, I am repeating these things so many times that now you know by just looking at the model. So, this is V in is equal to sine omega in t, V out is cosine of omega out t. What we are going to find out that what are the different ranges, frequency acquisition ranges for this particular PLL. This is V error, this is V control. Okay. Now, in this case we have worked out earlier that our V error used to be 1 by 2 into sine of omega in plus omega out times t plus sine of omega in minus omega out times t. Okay. Now, in this case, to begin with, we need to find out what are the frequency acquisition ranges. So, I will use, let us say at t equal to 0, you have omega in equal to omega, okay, and omega out, which is always given by omega free minus plus k VCO times V control voltage. At t equal to 0, Vc is equal to 0. So, omega out is equal to omega free. Okay, if that is the case, we have frequency error between omega in and omega out. So, I will write that as delta omega as omega in minus omega out, which is omega minus omega free minus k VCO times Vc. This is what we have. Now, given this frequency error, we know that our phase error at any given time is equal to integral of the frequency error with respect to time t. This is the phase error. So, let me work out this. What is the phase error here? Phase error is using our previous equation, phase error of time t is equal to 0 to t. This is frequency error, you see omega minus omega free. So, I am calling that as omega 0. Okay. Omega 0 minus k VCO times Vc and integral of this with respect to dt. Now, in this particular example, you know what is the phase error for this. We know the PLL will be locked, PLL is locked when the rate of change of phase error with respect to time is equal to 0, which is this is equal to 0. Now, if you look at it, d phi error by dt from previous equation, which I will denote it as phi error dot, is equal to delta omega 0 minus k VCO times Vc. Okay. And what is Vc in our case? Vc is actually, you are using a loop filter. So, if we are using a low pass filter where with R and C like this, where the filter bandwidth is larger than the frequency error which we have, okay, then in that case I can write Vc as half of sine of phase error at any given time, where half is your KPD, the phase error detector gain. So, writing it again from the phase error derivative equation, this is equal to delta omega 0 minus KPD times KVCO into sine of phase error. Okay. So, your PLL is going to log only when you have a solution for this equation, right. So, what I will do, I will try to find the solution of this equation. Now, you see here we are taking the derivative of the phase error, and phase error is in the argument also. So, to find the solution, one easy way will be that if I look at this metric phase error dot divide by k, which is equal to delta omega 0 by k minus sine of phase error. If I equate this to 0 and find the solution for the phase error, then I can say I have a solution. Here your KPD times KVCO is written as k. So, now just look at if you have a solution. So, I am going to plot phi error dot by k with respect to phase error. Okay. So, with respect to phase error, phi error dot by k, you see that you are having minus sine of phase error here. So, delta omega 0, that is the initial frequency error which you have, k is constant. So, this is quite simple. So, what you will see here is you will have inverted sine shifted by delta omega 0 by k. Okay. So, what you are going to see here is, my plot may not be the exact sine wave, but that is what you are going to see. Okay. Here this shift, whatever shift you are seeing here, this shift is nothing but delta omega 0 divided by k. So, in order to find the solution for the above equation, we need to just know wherever this variable equals to 0, and we see that you are seeing two such points. One is this, other is this. So, the equation phi error dot by k equal to 0 has two solutions as shown in the plot. Okay. I call this as N1, this the left one, and the right one I call as N2. Okay. We are not making any approximations here in the solution. So, there are two solutions N1 and N2, null N1 and N2. We need to find which is the stable solution. So, whenever you solve for some roots, right, you always validate whether the roots are correct or not in any given equation, or whether the solution hold. So, in this particular case, you see that there are two solutions N1 and N2. Other thing which you also observe is that the solution which you are seeing, the two solution exists that exist only when delta omega 0 by k is some particular value. You may not have solutions always. Okay. So, the solutions exist here only when you have delta omega 0 by k, right. If you take this up, the shift is on the upside, then you will know that sign of phase error is going to limit the nulls at this point. You are going to have solutions only when phase error by k is actually less than equal to 0, then only the solutions exist, which implies that delta omega 0 by k is less than equal to sign of phase error, and at max the sign of phase error can be equal to 1. So, a solution exists only under this condition, but there are two solutions. So, the question is which solution is the correct solution here, or both of them are correct, or one is correct, which one is correct. Okay. To find that, what you need to do is you need to look at this curve. So, let us look at one by one. From our solutions, what we see that there are two things which we need to find out, which we need to make sure that a solution exists for the above equation, for the above plot. First thing is phi error dot by k in above case, which is equal to delta omega 0 by k minus sign of phase error. This is less than 0, less than equal to 0, only then you will find that there are solutions, and this will happen only if delta omega 0 by k minus sign of phase error, or we can just shift the sign. This is less than equal to sign of phase error, which means there is an upper limit on the frequency error which you can have, which is k. Sign of phase error at maximum will be equal to 1. Okay. Similar limit exists on the other side of omega input. The another thing from which we see from here is that there are two solutions. Okay. And there are two solutions which include null 1, including, so far we say there are two solutions including null 1 and null 2, null and 2. Which of these solutions is a stable solution? That is something which we need to figure out, right. So, now let me just plot what we have seen before in a little bit amplified manner. Okay. So, I have this thing here, I will just plot here. Okay. So, what I am plotting is, as you see in the previous page, this is phase error and this is phase error dot by k. There are two solutions, as I told, one is null n1 and other is null n2. So, let us look at the solution null n1. Okay. So, for this particular phase error, I call this as phase error 1. For this particular phase error, you see that your derivative of the phase error is equal to 0. So, you may think that this is a solution. Now, a solution is a stable solution only when, if you make any disturbance to the system at this particular phase error, the system returns back to n1. If you are looking at the stability, so I will just give you another example, that this particular system here, let us say if you have a ball in the valley and you move this on either side, it will come back to the center position, right. So, the ball is actually stable in the valley at this point, right. Similarly, if you have a hill and you keep a ball here and you make a small disturbance in the system, it will either roll this way or roll the other way. So, the ball here is not in equilibrium, it is not stable, whereas a ball here in this case is stable. Similar analogy will apply here. If N1 is a stable solution or the phase error 1, it is a stable solution, then in this particular case, if we make a small disturbance at N1 position. So, how we are going to make a small disturbance at N1? At N1, I apply phi error is equal to phi error 1 plus delta. So, you make a delta change in the phase, you can apply the disturbance. If you apply the disturbance, then looking at this particular curve, what you see is that the derivative of the phase error is negative, phi error dot is less than 0. So, you increase the phase error, but the slope of the change of, or you can say the slope of the phase error is actually negative with respect to the phase error, right. Phi error dot is actually with respect to time, it is negative. So, phase error will reduce. Okay. I hope you understand this part. At null N1, if this is a solution, then you know at phi error 1, your phase error at exactly at phi error 1, your derivative of phase error is equal to 0. But at phi error greater than phi error 1, which is like you make a disturbance, you get at this delta phi, what happens is because the phase error, the derivative of the phase error is negative or the slope is negative, you will reduce the phase error. So, if I have a variable, any variable, let us say dx by x is a variable and dx by dt is 0, right. Dx by dt is 0, it implies that x reduces with time, and reduces with respect to time when the slope is negative. Similarly, I made a change to the phase error or I applied a small disturbance at N1, but because the slope at that particular point, which particular point? This phase error 1 plus delta. This particular point, the slope is negative, so phase error will drop. If phase error drops, what will happen? It will come back to N1. Similarly, if you make a small disturbance on the negative side, if phase error happens to be, I made the disturbance and phase error 1 is minus delta phi, since phi r derivative is greater than 0, your phase error will increase. Phase error increases, that means you come back to N1. So, N1 is a stable solution here, because if you make any disturbance in this particular case, it moves back to the same point, right. Now, on the other side, you look at N2. Okay. If you look at N2, then I call this solution as phi error 2. At phi error 2, phi error dot is actually equal to 0. So, it appears to be a solution, but if phi error changes from phi error 2 to phi error 2 plus delta phi. So, I made a small change on this side. The slope of the phase error is actually greater than 0. you move from 0, the slope is positive. If the slope is positive, what will happen? The phase error will increase. So, you move away from node N2. Similarly, if phase error changes from phase error 2 to phase error 2 minus delta phi, because your phase error dot is less than 0 on this side, the phase error will reduce. That means, you go away from N2. So, N2 is not a stable solution, stable point or stable solution. Okay. So, what you see here is that there exist two solutions, there exist two phase error values which give you the derivative of phase error equal to 0, or you can say a solution exists, right, even when you start with the frequency error in the PLL, but out of those two solutions only one solution is stable. Okay. So, you may start your PLL, it may start with 0 or some other point, finally, it will come to N1, okay, in this particular scenario, right. Now, there is one other important thing. I have not drawn the full sine wave, but if you look at it, you will see a sine wave, because I can plot, there is nothing which is restricting me to how much on the phase error value I can plot. So, I can plot for a lot many values. Here you see that these solutions N1 and N2, they do not exist only at two particular points in this plot, but there are many such points, right. Sine wave is periodic in nature and you see many solutions. Okay. An important observation here is that between every two peaks, you can do it either way, between every two peaks there exist two solutions given by N1 and N2. Out of those two solutions only one is stable. Why it is important? It is important that when you start your PLL, during the start of the PLL, you can start from any phase error. I can start from here, I may start from here, or I may start from only this point, maybe sometime I start from here. These are the initial phase offset which you can start with. So, if I call this as phi error 0, this can also be phi error 0, well, this can also be phi error 0 and this can also be phi error 0. Okay. So, you can start from any point. Important thing here is no matter where you start, okay, if you start from this point, this particular point, then your system will, your signal will change in the PLL and finally, you will find a solution at N1. If you start from this particular point, right, then you will again find a solution at this point. I call this as N1 dash. Within every 2 pi phase difference, so within every 2 pi phase difference is like within every 2 peaks, you see there exists a solution. Okay. So, how this span is 2 pi, and within this 2 pi span you see there are two such nulls and the stable null is this particular one. You look for the other one, if you start anywhere between at this point or this point, you have a solution here. Okay. What does it mean? It means if delta omega 0 by k is less than equal to 1, there exists a solution for phase error between, you can say, phi offset minus pi and pi is phi offset, whatever phi offset you start with. So, there is always a solution in this range of 2 pi. So, if you start your PLL with initial frequency error and a solution exists, then your PLL will always lock, and it will lock with phase error without exceeding 2 pi. Okay, so, this is important. In this type 1 PLL which we have been discussing, right, for the type 1 PLL which we have been discussing, in this PLL, given the frequency error, if there exists a solution which will be limited by your delta omega 0 by k less than equal to 1, if there exists a solution, the PLL will always lock and without the phase error exceeding 2 pi, which means the phase error does not exceed 2 pi and the PLL locks. So, lock in range is equal to, lock in range is actually equal to delta omega L, which we call, and this is k, which is k PD times k VCO. This is the lock in range of the PLL. I will demonstrate this with the help of simulations, which you have also seen somewhat before, but not directly in this particular context. Okay. So, what we mean here is, let me show that. Okay. In the first case, we have our initial frequency error as given by delta omega 0 into 2 pi times 5. Okay. Mega radians per second. So, the important part here is that the phase error is small, and in this particular example, I was using our lock in range delta omega L as equal to 2 pi into 50 mega radians per second. Okay. So, this was the lock in range given by KPD into KVCO, and the initial frequency error was delta omega 0 into phi. So, what you see here is that the phase error starts from 0. This is the phase error starts from 0 and it settles to a value. Okay. It does not go close to 2 pi at all. Phase error does not reach even 2 pi. Okay. It settles because the frequency error was small. Then, when I increase the frequency error, in this case, I increase the frequency error from 10 pi mega radians to 80 pi mega radians. So, this is 2 pi into 40 mega radians per second. I increase my frequency error to this value, and what you see here is that our phase error increases and it actually settles. This also does not increase more than 2 pi. Okay. You have seen the error voltage in both the cases earlier, but the important point which you observe is that the PLL locks without the phase error exceeding 2 pi. Now, what happens if the phase error exceeds 2 pi? Let me show you. So, in this case, I am showing you for two different cases. One, delta omega 1 of 0 is equal to 49 2 pi into 49 mega radians per second. Okay. And other cases, delta omega 2 of 0 is 2 pi into 50 mega radians per second. Okay. This is the frequency error. The one which you see here is for the case the red one, where you see that this particular red one is the case for delta omega 1 0, and this one is the case for delta omega 2 0. Okay, these are the phase errors. So, this one is for delta omega 1 of 0 and this one is for delta omega 2 of 0. So, what you see here is in closed loop, for the first case delta omega 1 of 0, the phase error starts from 0 because the initial offset was 0 and it reaches to this value. okay, which is 0.2181 times 2 pi. It does not reach 2 pi at all. Okay. Whereas, in the second case which you see, the phase error value is very well 1.25 times 2 pi. So, the phase error exceeds 2 pi, because the phase error is larger than the our lock in range. Here we are actually having not 50 megaradians, but 51 megaradians per second, 2 pi into 51. Okay. So, there were two conditions which we initially told, that delta omega 0 by k should be less than 1, okay, and we told that there always exists a solution within the phase error of 0 to 2 pi. If you exceed that, right, the PLL will not even lock. So, that is something which we see here is using three different examples: a low frequency error, then you have a little large frequency error, and then very close to the lock in range. So, very close to the lock in range, you see phase error exceeds 2 pi and the PLL does not lock. The PLL does not lock, how will you make sure? Because the corresponding error voltage is shown at the bottom, and you see the corresponding error voltage does not settle, it just keeps on repeating. Why is it doing this kind of weird behavior is something which we will check out. Okay. You want to understand in case why there exists no solution? Well, you have already seen the other plot, where if delta omega 0 by k is greater than 1, then in that particular case you may see the same plot phi error dot by k as something like this. Okay. There are no, there is you do not see this particular plot crossing phase error axis at all. Okay. So, there exists no solution. Okay. Thank you.